we're going to finish off talking about threads, and I have something I want to say that we never got to about page tables, page directories, and then today we'll go on and talk about scheduling for processes. So one thing that you should know when you're dealing with concurrent programming, right, where you're trying to have one or more threads that are working together to do some calculation, is that there can be reordering, that the order you see stuff happen in your source code is not necessarily the order that it executes. Okay? One thing you're all aware of is the compiler. Right? The compiler can reorder code kind of to its heart's content as long as it maintains correctness. And when it does for C, correctness, it totally ignores anything about any other threads that might be running. Okay? So that's why if you have a loop that's doing checking some memory mapped I/O value, so while status equals 0, do nothing, the compiler can, so that's really hard to read, equals 0. The compiler's perfectly happy to just check that once and decide whether it's an infinite loop or not, right? And so you need to do something special to the compiler to tell it, no, actually, status is pointing to a volatile, and therefore you need to check it every time. But that reordering can happen. Examples would be it can hoist code out of a loop, right? That happens so that stuff that would normally happen in the loop is happening before the loop and not each time. But the other weird thing is that the CPU can reorder as well, right? So you have these assembly language instructions that either you wrote or the compiler generated for you, and the order in which they execute need not be the order in which they appear in the source. Okay? So that can be difficult to reason about and difficult to program, but that is where we get some of our speed, right? Without that, if we have to execute things in strict order, then it really harms the speed. So,
are there any situations where you optimize your own code and then you want the assembly instructions to be exactly that because you want it to be optimized to what you made it? Like it does it in a different order without your, like, you kind of get what I'm saying?
Well, let me tell you the solution of how we deal with this. So the way we deal with this is we kind of say, okay, now let me give you an example of where this might happen. So let's say we have move *3, 3, or do we put a $sign? I don't remember, into what is it, %EAX, and then let's say move EAX into some memory address, and again, I don't remember because I never write assembly code directly. So I'll write it in memory address 1, 2, 3, 4. And what else do I want to do? OX 4, 5, 6, 7, 8. Okay. Let's say there's another program that is looking at the value of 1, 2, 3, 4. Okay? And actually, let's say increment EX somewhere in here. EX. I don't think even increment is a x86 instruction, but let's pretend it is. So what you'd expect to see here is, let's say 4, 5, 6, 7, 8, whatever's at that address, starts out life as 1 more than this. Right? You'd expect after these instructions, it's still 1 more than that. And you certainly wouldn't expect that this one is going to be executed before this one. But that's exactly what can happen. Within your program, you can't tell the difference. Right? That's kind of a key of how this works, is within your particular, this piece of execution, you can't tell the difference. But if you've got something running under the CPU, or you get interrupted somewhere in here, stop, and then resume execution, someone can see an ordering that's different from what you expected. The set of allowed behaviors is called a memory model. So x86 has a memory model, Java has a memory model, C has a bit of a memory model. Okay? And there are some things that can prevent reordering. Or another way to think of it is that will ensure that the outside world, everything will be synchronized up to that point. So exchange, which we talked about, does this swapping of value into memory location. And there are also calls where you can add this memory barrier. So the memory barrier basically says don't move stuff. So we got here, we've got some code. We can add a memory barrier here. And then we can have more code here. And what that says is all this will be executed and externally available before we start executing any of this. Does that make sense? So how do you generate a memory barrier? Remember we talked about, very briefly, prefixes you can add to opcodes? Well, one of the prefixes you can add is, I'd like a memory barrier, please. Actually, there's not even a please. It's just, I want a memory barrier. Okay. And so there is if you're using locks, you're kind of okay, because when you lock and when you unlock, there are memory barriers, implicit memory barriers. I think because the exchange, we'll be using exchange, at least for the locking, and the unlock will also have memory barrier, so that things will be visible outside, so that everything that happened in the critical region will be visible outside before you unlock. Does the concept make sense? Okay. There are data structures you can write that are lock-free data structures. So you can have, for instance, hash maps that allow you to concurrently read and write, and they do stuff fancy to make that work. And part of what they need is to know when things are happening. And so there, they may very well need to be adding memory barriers in order for that to happen. Okay. The spin locks we talked about, right? So we're wasting time in this CPU. And the idea is, if you're just sitting there waiting for a lock, and you're going to be waiting a while, why not just let someone else run? Okay, so that would be called like a sleep lock. So have this, let's say, thread in the kernel go to sleep, let some other thread run until whatever the thing it was waiting on wakes up. So spin locks you really only want for very short critical sections, not for long ones. For long ones, you'd use a sleep lock or a blocking lock. Commonly, they're more expensive, but they give this important ability to yield a CPU. Questions on that? All right. And it is really hard to find concurrent bugs, or really to find all of them, because usually what happens is you have latent bugs in there, intermittent bugs, and it's very hard. Right? Your goal is to turn your intermittent bugs into mittent bugs, right? Ones that happen all the time, but it can be very difficult. And there are some tools that can help you. Race detectors, things that will run your program dynamically in different ways. There's static analysis that can happen on your program where you say what things are being protected by what locks, and you can have static analysis that verifies that that's true, that you're never trying to, let's say, read or write a value unless you have a lock. Okay? But it's hard. This is hard, for sure. And if, again, a big thing would be if you can have immutable data structures, it's so much easier to reason about your programs. Yeah.
So when you say exchange prevents reordering, is that just if I looked at the x86 manual somewhere, I'd find that?
You'd say it's automatically, you can throw the prefix in front if you want, but it's automatically there, by default it's there. Okay, 2 lab things. Let's see, is it 2? Yes, 2. Thing number 1, challenge. So let's see, greater than or equal to 1 challenge problem is required from lab 2 on. That was part of the lab 2 instructions. So know that now. It's not necessary for 3A and 3B. Just make sure for one of those you do a challenge problem. And similarly for 4, I'm pretty sure that for the A, B, and the C, we only require the one challenge problem as well. Yes?
So like for lab 3, if say we didn't do one last week, can we still do the one last week? Like in the
No, that one's over.
Okay.
You have to do 3 Bs. Let me think about this a second. Is that okay?
I would definitely have spent time doing the 1 through 3 if I knew that.
Yeah. All right. You can do a 3A one if you want. Okay? This time. And then for 4, do it whenever the week is due. Does that make sense? Second, some people had some, totally understandable, had some issues with the 3A where it's not working 100%. And so I will give you a solution to 3A so that you can continue on and not have be stuck. So I will probably, in a very low-tech way, just email the mailing list and send you a copy of the files. in.c, trap.c, trapentry.s. I could set up Git and add you as collaborators and so on, but it'd be a pain in the ass, so I'll probably just do that. Okay. Questions on that? So solution to lab 3. Available. And you should have all seen, many of you have, lab 2 is graded. I think there was some back and forth of a couple things. I think it's all completely up to date. So if anyone has any questions, they can let me know afterwards. And I had just started on lab 3. Okay, processes. So we had, today's homework is on locks, kind of what goes wrong if you don't have interrupts off when you're doing an acquire and a release. So let's just take a look at that. So in id.c, was it an IDE read-write? Is that where we were doing this? Okay. So after we acquire the lock, we want to, yep. Okay, then we get a panic in acquire. And like, what do we do now? What we do is we look at these numbers, and that's our backtrace. And so we just look in our assembly file and figure out our backtrace, right? So here, okay, well, this is calling panic, fine. And here, we are in our interrupt routine, right? So we're in our IDE interrupt, which kind of makes sense because our lock protects IDE interrupt and IDE read-write from happening. And our IDE interrupt, is it reasonable that an interrupt routine got called when interrupts are enabled? Yeah. Would this interrupt have been called if we had not had interrupts enabled? No. If you don't have interrupts enabled, interrupts don't happen. So we are going into our interrupt. And we're acquiring the lock. Well, in fact, let's just look at the panic acquire for a second. Where's acquire? Oh, it's in spin lock, right? All right, so we actually, why do we have a panic? And the reason we have a panic is we are holding the lock. Actually, who's we? The current CPU, exactly. Because a different CPU could be holding the lock. But it's not like we're talking about multiple threads. It's the CPU. So this CPU is holding the lock, which makes sense because the CPU executed ID read-write. We acquired the lock, and then we enabled interrupts. And now we see what happens. That we come back in, and we're trying to reacquire the lock when we already have it. And that's an error. I don't know why. What if this, maybe this is the issue. Maybe we should just say, it's okay if you acquire the lock while you already have it. How bad can that be? So let's try that.
Well, that must be a deadlock.
It looks good. Let's see. Maybe it's intermittent.
I mean, if the ID interrupt doesn't happen when you're running ID rewrite, then you're not going to get it.
I would, well, let's see. So something's wrong.
If the ID interrupt happens while you're running ID read-write, it'll try to acquire the lock. But since the lock won't be released until you return from the interrupt and ID read-write finishes, it's just going to wait forever trying to acquire the lock.
So it will, here says, so let's see, what happened here? Adding is we failed in acquire, called from IDE interrupt, because we were already holding locked. All right, and I swear I thought this failed differently. But no, is this how it failed? Did you guys try this?
I think sked locks, which happens a lot less frequently than acquire.
Yes, yes. All right, so let's reason about this then. So explain again.
So basically, if we acquire the lock in ID read-write, and then we get an interrupt, and then in the interrupt handler we try to acquire the lock again, since the lock's already held, we can't acquire it again.
Yeah, that is exactly, that is right. So IDE interrupt tries to acquire the lock. Right? It called acquire. We saw it called acquire before. And we checked and said, wait, do we already hold it? Because if we're already holding it, it's going to be really hard to get it. Okay? Because we're going to be spin locking. Right? We're going to sit there waiting. And the code that holds the lock, which is also running on our CPU, will never be able to run. Right? In our case, we're in an interrupt routine. No other interrupts can happen. And so we are going to sit here, there, forever. Right? Make sense? Which is not good. If an interrupt happens while the lock's being held. As we say, if an interrupt doesn't happen when the lock's being held, we'll just go through, we'll get our $sign, we'll go on our way, unless some other IDE problem happens. So definitely an intermittent bug, but happening reasonably often. Looked like it happened maybe 20% of the time, 30% of the time, something like that. Miles. What happens to the interrupt, right, in our original code, where we have interrupts off? Forever. Yeah, so think of it this way. There's a line on the CPU. This is certainly true in practice in the past and conceptually, at least now. So we have an interrupt line. And it gets held on until this interrupt's been serviced. And our fetch, decode, execute cycle always checks this before we go. Always unless interrupts are disabled. So we go through, we do all of our stuff in IDE read-write, and eventually we want to release the lock. Interrupts are turned back on. The absolute next instruction is going to look and see the interrupt is there, and it's going to service it. So we won't lose the interrupt. It's going to just be delayed. Make sense? Okay. And what if our ID interrupt happened on a different core? TUI. Let's say we revert our code, so it's back to how it was. First off, when I turn off interrupts, am I turning off interrupts on all CPUs? No, just the CPU I'm on. So I'm on CPU 0, let's say. So we'll have CPU 0 will be the IDE read-write. And let's say CPU 1 gets an interrupt, and we call IDE interrupt. What'll happen?
Sorry, you call it.
So we call it.
CPU 0 runs IDE read-write.
Yeah, it's in the middle of doing that, and it's holding the lock right now. And then an IDE interrupt comes in, CPU 1 chooses to handle it. We're in IDE interrupt. We know it's going to call acquire on that lock. What'll happen?
Won't it take its own, won't it still run the same issue? Won't you?
Here's why it won't. So we're going to check whether we're holding the lock, and we're not holding the lock, right? Because 0 is holding the lock. And it's going to sit there, spin, 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 spin. But this guy's going to be running too. And this guy will eventually finish and release the lock, at which point this guy will get it, or someone else who's waiting on it. Does that make sense? Okay. Jonathan.
When you disable interrupts, is the interrupts queued? And when you enable interrupts again, it'll interrupt?
That is correct. When interrupts are disabled, basically the interrupt is queued. Yes. Now, keeping interrupts off for too long can be a problem. I'll give you an example. Serial devices, like you may have seen in the past, which used to be very prevalent, like modems and stuff like that, used to work with a chip that had like a buffer of 3 characters on it. So basically, when you got a character, it would interrupt the CPU. And if another character came up, it would put it in its buffer, and another put it in its buffer. But if the CPU didn't get back in time, you would lose bytes. Right? You could configure it how to drop it, but it'd drop them because there's nowhere else to go, and it's getting this data real time. Does that make sense? So it's not that nothing bad will happen if you just ignore interrupts for a long time. The interrupts will still happen, but it may be that you've lost data in the meantime. Andy.
Does the holding function only check, like, how does it check that on, like, that CPU?
Let us take a look. Holding. We have in the lock a field which is the CPU. So that's what it does. And let me go back and fix acquire because we're going to want to be doing some other things. So that is that. And then okay, so that's fixed. In acquire, we don't disable interrupts and re-enable interrupts explicitly. We push, or we keep track of, how many nested times we've been asked to clear interrupts. So let me give you an example. Let's say we acquire A lock, and we acquire B lock, and then we release. We'll even release them in opposite order just because that seems prettier. And we do some stuff in the middle. Okay? If we just turned off interrupts in acquire, and turned them on in release, we have a problem. Because what would happen after this release? What would be the state of interrupts? They'd be back on. Bad, 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 bad news, because we're still holding the A lock, and we're not allowed to. So therefore, acquire is going to push how many times have we set. So, and it actually doesn't quite do that. What it does instead is, in the acquire, in the push, it checks to see whether interrupts are enabled or not. So basically, it's going to restore them to, it saves the state and restores it when it's done. That's what it does. So the outer one is going to save the state of A, and the state is going to be interrupts are enabled. And when we restore, interrupts are going to then be enabled again. But B is going to say, oh, interrupts are disabled. So therefore, is it just cleanliness that I released them in this order? If I acquire A, acquire B, release B, I've got a large problem. Because again, the release A is going to take us back to the state we were at when we acquired A, which is interrupts enabled. So we have...
Why? It looks like, looking at the code for pop CLI, it looks like it would just...
let me look at this.
The NCLI down to 1 and not do anything, and then when you release B, like it looks like it's only the number of push CLIs and pop CLIs that count, not like which specific one of this.
You are right, because we're sharing this information. So, yeah, that is a good point. So the interrupt enable, the first one is going to save what this value is, and the last release is going to restore it. So it's not quite what I said, that the acquire gets the state and the release restores the state. It's a smarter one, which is the first acquire gets the state and the last release restores the state. So the order of these don't matter. I still think acquiring, releasing in opposite orders is clear.
So if interrupts are going to be disabled for the entire duration of this, why when you just use one lock as opposed to two? I don't know if that makes sense.
Oh, why might I have two locks? Because I'm operating on two different things, right? And by having finer grained locks, I can have more concurrency. Because I might, let's assume here we need A and B, and some other part of our code we just need A, and some other part we just need B. Then we got more concurrency we can do. Because the one that needs just A and the one that needs just B can both be running in parallel.
Yeah, okay. And regardless though, you will your interrupts will be disabled for a long, for the same period of time.
Yes, for the same period of time,
And
whether you had one or two.
And is the reason why you want to minimize the amount of time you hold on to a lock? It's one of the main reasons is to minimize the amount of time that you can't have interrupts.
There's two ways to think of it. One is you want to minimize the time that you can't have interrupts. And then the second reason you want to not have the locks for very long is because while you have that lock, someone else who's waiting in the lock is just sitting there spinning, doing nothing. Right? It might be an actual CPU. Well, it would be another CPU spinning, doing nothing. If we're holding the file table lock, all right, so let's look at this one. This was in file.c, I believe, right? No, it wasn't in file.c. All right, does anyone remember where the file table lock is? It is in file.c? Got it. You mean like this ftable.lock, yes. All right, so in here, while we do the alloc, we'll do a, no, I want clear interrupts, right? Is that the order I want? There we go. Set them, turn them on, clear them.
And then you hold it and clear it.
What does it stand for again? Like the acronym for each?
Make sense? All right, let's try that. Oh yeah, what do we got to include? Thank you. All right, and it's working good. And we'll do it again, and it's working good. And we'll do it a third time, and it's working good. And we could do this quite a few times, and it'd be looking good. But we still have an intermittent error. And we can see that if we go ahead and run in GDB and break in, was it file_alloc? No, it's not file_alloc.
No underscore, just.
Thank you. And let's just wait a little bit. And we're okay. All right, this is not what I remember happening. Let's see. When we set that breakpoint, stop this again, and let me do it one more time. We're doing break 34. There we go. We got a panic. So it's, as I say, more mittent. So now we need to figure out what's going on. The 7B9 is probably the panic. This one is in our release here. So let's look back in our release, and actually we get a panic on schedule locks. So
Well, the previous error was not on the release, it was on the sched function that was called right before, right?
I don't actually, you mean this one?
No, second one.
So this is,
It was the
yeah, this is in yield, right? Well, actually it's a call into schedule. Yeah, so. Okay, so our problem is we're calling skip, so let's just look at this a second. We're in the scheduler. We're supposed to hold only the p-table lock. So what happens must be we got an interrupt because we enabled interrupts. We decided to call the scheduler, which just gets into today, and we decided to run another process. Okay? And so this other process, we're going to go in and start running them. But first off, we just want to check a couple things. We want to make sure that we are holding the p-table lock, because that's a requirement on the process table of this method, and we are. And then we want to make sure no other interrupts, no other locks are being held. And so we look at that push count to make sure it's 1. And that's the problem. So we would be holding this lock while we were no longer the running process. And that would be a bad thing. New processes could acquire it. Other CPUs could still sit waiting for us. Yeah.
Sorry, NCLI refers to the interrupts being disabled.
It's the number of clear interrupts that have been issued by the locking, by acquire. Okay, questions on this? Yeah.
So every time a new process begins, it will try to build context function?
Yeah, this will be for every time we're doing a context switch. We're going to be looking at Schedule in a lot of detail today. Katie.
Is the CLI just the total number of interrupt clears, or is it the number of interrupt clears without a corresponding to flip back on?
It's the number of pushes without a pop. It's pushes minus pops, I guess is the best way to put it. Yeah.
Would the behavior be different then if we use like push CLI instead of just CLI? When we like in the file allocator?
So in the file allocator, if we did push CLI, and then in a corresponding pop CLI late, well, hold on a second. So let's go back and look at that.
Because like in that case, we just haven't been changing the end CLI.
Yeah, but it still changed on its own,
Yeah.
right? Because we went and acquired another. We have another lock, right? Basically what happened is our interrupt happened in the middle of this, and so therefore we still have the F table lock. So it wouldn't really matter whether we had called push or not. So, and it wouldn't work very well because this would have to be like a pop CLI, which is not clear that would work. Other questions? Okay, so basically what happened, the reason we got a panic now is because we had a very long time that we were holding that lock. Basically all the time we were sitting there in GDB. So process. We talked about this before, but we've got this abstract virtual machine with a CPU and memory. We want this for isolation so that we can have isolated units of computation that can affect other units of computation. Our API, fork exec, wait, kill, sbreak, and get PID. XV6? JOS, Ashley? Is this XV6 or JOS, this API? Yeah, this is XV6. So fork is our one way of creating a new process. Exec replaces the currently running process with the currently running code in a process with new code. Wait waits until a child process is finished. Kill kills a process. Sbreak allocates some contiguous memory, and get PID returns your PID. So there are, of course, more system calls in bigger type Unixes or Linuxes, but this gives us a sort of a bare minimum that we want. All right, so we got more processes than we have processors. That's why we need to do this multitasking. So let's say you have two processors and you want to run your editor, run your compiler, and play some music, all roughly together. Why you're editing and compiling at exactly the same time, I'm not sure, but let's say we are. You're editing, let's just say we are. Just go with that. Okay? So we need to multiplex n processes among m, possibly less than n, processes. So processes on processors. Time sharing, context switching, scheduling, all sort of the same. It's the same thing. If we had more processors than processes, there's no problem. Each one is just runs its own process continuously. Okay? But it's only when we get to have more that we have this issue. We want it to be as transparent as possible to a user process. Okay? Other than the fact they're not getting as much CPU time. And as it will turn out, maybe it'll get just as much CPU time. Right? If I'm a process and I do a read to disk, I've got millions of CPU instructions that I'm just not doing anything with. I'm just have to wait for that read to finish. And so therefore, I'd be quite happy to let some other process go ahead and do its thing. Okay? So that if you have a CPU-bound process, it's only using CPU. But if you have an I/O-bound process, it's mostly doing I/O. And so it just has these bursts of CPU followed by I/O that takes almost forever. We want it to be preemptive. So we don't want to have a process have to call yield. Aaron, why not? Why do we not want a process to have to call yield?
Why don't we want processes to call yield? Because we don't trust the processes.
Okay, that's a good reason. So we are suspicious. Rightly so, right? That basically means your system works well if every single application makes sure to call yield every so often. And that was the way life used to be on, let's say, the Mac. And it was very easy for one bad apple to ruin the whole bunch. Yeah, I finally got it when I hear the laughter. It's like, what are you laughing at? And then I realized I was funny, unwittingly. And it's nice if we could be preemptive in the kernel, too. If we could do that, that's nice. So that within a system call, we can go ahead and switch processes as opposed to between system calls. XV6, here's what we have. We have one user thread and one kernel thread per process. Okay, so we don't support multiple threads in user programs. There's just a single thread that we provide. So we don't support, for instance, that pthread create, the whole POSIX pthread system. So one user thread, one kernel thread per process, one scheduled thread per CPU. So each CPU is independently going through when it's time to switch processes and looks and see, is there a process that is runnable, that is ready to run, but not running? And if so, it'll switch to that. And of course, if each CPU is going through looking at the processes, there better be some lock to make sure that they're not manipulating the same thing. Yeah, because I don't want you CPU and me CPU to both run that process at the same time. Yeah.
What's the consequence of having one user thread and one kernel thread per process?
So the one user thread and the fact that we don't allow any more than one user threads means that our kernel doesn't know anything about multi-threading within an application. Okay, we can't write. This is not 100% true, but roughly we can't write a multi-threaded application. So let's say this is an app, and we could have 3 threads of execution that are running.
Different processes.
Well, if we have different processes, then you can certainly have multiple processes. But if you want to have multiple threads within a single address space, you can't in XV6.
What would happen with the hash table assignment?
So in our hash table assignment, we weren't running an XV6. We were just running on Knuth. And we were using the POSIX threading library. Right, we had pthread create, so on. Yeah, so, Ashley.
Well, I guess I'm also a little bit confused about having like one user thread and one kernel thread per CPU. So like for example, if on a CPU the user process is running and then it makes a system call, doesn't it happen like it switches from user mode to kernel mode, but like doesn't this happen on like one thread? Like,
So here's what'll happen. We're running our one user thread, right? We've got our, editor. And we have our single thread, and we make a system call. That is going to then switch us to the associated kernel thread that is associated with that process. Okay, so it'll have its own stack. It'll have Basically, that's what the thread is, stack and registers. So we'll be running on that kernel thread within the kernel, and it's running on behalf of this user process, of which we have one thread in it. These threads in the kernel can be multiplexed. Okay, they can be time shared. So we'll switch from one kernel thread then to another kernel thread. And that kernel thread will return back to the user program, its user program. And then that user program will either explicitly make a system call, or a timer interrupt will happen, or I guess it could be some other type of interrupt. It will come back into the kernel, rerun its kernel thread, swap to do something different. Eventually we'll come back to this one and return. Does that make sense? Right on.
So when we were doing JOS, I was reading about how the kernel stack is really small, so there's a lot of things you can't do in the kernel. But if we have all these kernel threads, like one per process, and we have a stack for each of them, isn't that going to use up all the stack space?
So your question is, and in JOS has a different setup, right? JOS doesn't have one kernel, it doesn't have a stack per process. It has a single stack per CPU. So we have, right, CPU 0 has a kernel stack, CPU 1 has a kernel stack, and so on. And those are a fixed size, and therefore it's limited what you can do. This is XV6 specific, yeah, definitely XV6. Pascal. So if we have 3 processes and 2 processors, how many threads do we have? One user thread per process. So we have a total of 3 user threads, right? How many kernel threads? We've got 1 user thread and 1 kernel thread per process. So 3 processes gives us 6. Okay, so yeah, 3 user threads, 3 kernel threads, 6 threads. And then how many scheduler threads? 2. Yeah, 2 scheduler threads. Okay. Oh, I was just thinking. It hadn't happened, and I was so happy. I think what it is when I scroll too quickly after drawing, that it buffers because I can't even save this as a local file. It saves somewhere in Microsoft Cloud. And so I think until it gets the stuff to cloud, anyway, we're going to just leave it right there for now. So what is a thread? Here's our definition for XV6. It's going to be either we have a CPU core executing, right? So we have one CPU executing, and it's got a stack where the stack pointer points, and it's got other registers too. And that's our value, and that's our thread. Or it's a saved set of registers in stack that could execute. So it's either the current values, or we've saved it so that we can come back to it later. So that's what we need to be saving, basically. Saved set of registers and a stack. So what's going to happen? We're going to go from user to kernel thread. Dave, what are the ways we can go from a user to a kernel thread?
Well, you would need to have some sort of way of switching the registers and stacks.
Yep, and plus if we're in a kernel thread, we're going to be in kernel mode.
Yeah.
So what's our one way we know to get from user mode to kernel mode? You can use a lifeline.
System calls.
Okay, system calls are one way. Interrupts are the most general way, right? So this is going to be, I guarantee you, this is going to be an interrupt. And either our int40, which is our system call, or some other interrupt. And it could be an I/O interrupt, or it could just be our timer's gone off. We better make sure to have a timer. So, does that make sense? Okay, so the kernel thread is going to yield. The kernel thread is going to yield either because it issues some I/O and needs to wait for it, or due to preemption, right, because of a timer, because there's something else basically that needs to run. So in the kernel, our threads are using, we have an explicit yield, and they will explicitly yield. Okay? So if you just start running a kernel thread, it'll keep running. Yeah, and it won't get preempted. So it has to explicitly yield. But processes don't, right? Processes, no matter what you do, eventually the timer will come up and it'll go to the kernel. And the scheduler, so the kernel thread is going to call the scheduler thread. Right? So we're running the kernel thread, we're running the editor. We were in the editor process on the user thread. We, let's say, made a system call, or let's just say that timer happened. So timer happened, we're now in our kernel thread for that same process, and it is going to call the scheduler. The scheduler then goes through our table of processes and tries to find one that's runnable. Okay? What if there are no runnable threads? Is that possible? In the scenario I gave you, it's not possible, because I'm running a process and it got interrupted due to the timer. So if it got interrupted due to the timer, is it runnable? I mean, in fact, it's running right now. And so it will be runnable. We want to put it back into the list of processes that when they get a chance can run. So worst case, in the case that we had a timer, is this process that just gave up time will still want more time. Now, if there's some other sort of interrupt, maybe that's not the case. Let's say we had a page fault interrupt, and we found that the user program was trying to access kernel mode. What might we do to slap that process on its hand for having tried to access the kernel? Jake. Kill. I mean, that's always my first response to anything, is kill it. So we would kill it, and therefore it would not be runnable anymore. And that's 90% true, because we're going to talk about killing and the fact that we have to actually run some code within that thread. But it's almost true. So if you don't have any runnable threads, what do you do?
I thought you said that it tries to find a runnable thread. That's what the slide says, right?
It tries to find a runnable, yeah.
Like in your example, you made it seem like you could switch back to the user thread.
It wouldn't go directly to the user thread. We always go from the schedule thread to a kernel thread. Okay? It could be this kernel thread that just called the scheduler, or it could be a different kernel thread that in the past called the scheduler and got put aside and didn't run.
But you can never go from a scheduler to a user.
You can't ever go from a schedule to a user thread. No. You always go to a kernel thread, and the kernel thread will eventually do a return interrupt.
So the only way to go back to a user thread from a kernel thread is through an IRED?
Or an IRED, yeah, yes, through an, that's the only way. Yep. So the schedule thread is going to call the kernel thread, and the kernel thread will go back to the user thread with an IRED. Okay, I'm tired of this. All right. Wait.
If it can't find
Brad.
the runnable thread, does it just wait? Or
What do you want it to do if it can't find a runnable thread?
either wait or throw an error?
Throwing it, so it is not, imagine this panic. Panic. There's nothing to do. you'd have to like work, make sure you always had something running on your computer, and enough to fill up all the CPUs. So we wouldn't like that. So what it often does is just keep spinning, looking and looking and looking and looking and looking. We'll look at that in a moment. The second thing you could do, and this is one of the challenge exercises, is like stop doing that. Power down your CPU, let's say. Or go into a low power state. Drew.
What's the timing come for the process? So say the process doesn't do an explicit yield, but it needs to give up, its time. So in this instance, it seems out of interrupts are way into the kernel thread. But does that interrupt also take into account just the hardware timer kind of going up for the process?
That is one possible interrupt, and the most common interrupt, I would say, that would cause your process to go back into the kernel is this timer interrupt that the kernel had to do before, right? You have to make sure before you give a user program control that you've got a timer set, because otherwise it might never return. Okay? Do you have a question, Aaron?
Can timer interrupts happen in the scheduler thread?
Timer interrupts, can those happen in the scheduler thread? No, I don't believe so.
Like, are interrupts just disabled while the scheduler is trying to time?
We'll have to look, well, almost. We'll look at it. The scheduler thread holds a lock on the process table for almost the entire time. It has to enable interrupts for a short period of time, but we'll look at it. Okay, what does states? Running. That means it's actually running on a CPU, right? And the fact is, we set that state to running before we go back to the user program, because we can't do it afterwards. So there's this short period of time where it's just about to be running, where we say it's running. Runnable means it's ready to go. Sleeping means it's waiting for something, usually I/O. Zombie means it hasn't been waited for. So we're going to talk about that too. And what's interesting is if you're in a zombie state, like all of your resources are still held. So if you, it is always a good idea to wait for your children. Okay? And then unused means there's just nothing in this particular process. Did you have a question, Dave?
Yeah, is there any benefit from keeping a process zombie versus killing it?
There's no. You always just have some overhead. We will see, what if you're a bad parent and you create some children and then die yourself without waiting for them? Okay?
Then, does it make sense to just go look for all zombie processes and kill them so you're not using resources?
Basically, but there's a clever approach that is used. So there's a parent of last resort, basically. So if it goes to the big one ancestor. In fact, what is the big one ancestor of every single process? Init. Right? Init was the very first process we created, and that's the one. Okay, it's hard to do context switching, right? Because there's a lot of moving parts. There's interrupts, there's locking, we got multiple cores going on, and then we also got to deal with terminating processes, and it's going to be a little bit complicated to do that. For preemptive switching, so I'm going to go ahead and run let's see, I don't want these CLIs. That's fine. I've got a program called Hog. Okay, Hog is very simple. It forks, and then if it's the child process, it has an infinite loop. And if it's the parent process, it has an infinite loop. Okay? You might say, why don't we just have one infinite loop after here? And the reason was, I wanted to have different instructions so I could differentiate the child from the parent. Because otherwise it's like, well, we're here at that same instruction, but I can't really tell which process it is. Okay? So if I look at hog.asm, you'll see here is the infinite loop for the child process at address F, and at address 11, we have the one for the parent. I am going to run make Knox GDB, and I'm going to run with one CPU. Gary, why one CPU? Why do I not run with multiple CPUs? What would happen if I ran 2 processes, 2 CPUs?
Each one will just get a process.
Yeah, they'll like run full out. But I'm trying to show context switching. So therefore, I need to make sure I have fewer processors than processes. Address is already in use. Let's see. That's why. Sorry, and I want to run hog. So run -hog -Knox -GDB. CPUs equals 1. That's not it? I thought that was it. I have a really long history. I guess I could have done a history 1,000. Okay, there we go. Okay, it's not in there. Why is it wrong? Okay. Echo Knox. Okay, there's more than one way to do this. Let's see. That's not it. It's not a knit. It's... Oh, of course, we don't have environments here. Okay, there's a simpler way to do this. Run. This is not how we do things on XV6. This would be great if we were using JAWS. Okay. We go in. We're going to set a breakpoint. Where do we want to set a breakpoint? Let's set a breakpoint at *F and 11. Oh, this is not exactly what we want because neither of these is our hog program yet. Because how do we run our hog program? Hog. All right, here we go. So we've got this infinite loop here. Okay, let's get rid of that one. And then we get the other infinite loop. So we were, in fact, doing scheduling. That's good. So let's see what happens. So we're going to look at switching to the scheduler thread. In fact, let's just break in switch. All right, so here we are in switch. The scheduler called switch. What's going on here? So the context, this is the context, and it holds the thread information, basically. So it holds a couple of registers, holds the EBP, holds the EIP. And these are always going to be on the stack. So since the context is on the stack, that kind of gives us the stack already. Dhruv.
Whose stack? The user or the kernel?
This is going to be the kernel. stack, because these contexts, these are always going to be stored in the, yeah, because the user could blow them away, and so that would be bad. So we're going to save this information. So we can see that we're saving EBP, EBX, ESI, EDA. We're saving the stack pointer up at the top there, and then we're writing into there. So that's basically saving the context pointer. We're not saving EAX, ABX, ECX, EDX. Why are we not saving those? Right? We've got a kernel thread that we're trying to switch. Don't we need to save the entire state of everything? No, because this is cooperative. Okay? It's cooperative in that it's calling, there's an explicit call to switch. So when you make a call in C, you know there are certain registers that are going to be blown away, right, that are scratch registers, that it's up to you to save. And so those C calling conventions will deal with that. Okay, so it's not the case that this switch can happen in the middle of any two kernel instructions. It's only well-defined times. All right. And we also don't save the instruction pointer either. So if we look at switch, switch takes a context, a pointer to a context, and says that's what we're switching to. And takes a pointer to an old context and writes the old context into there. So moving 4 of ESP and 8 ESP. 4 from ESP is which parameter? Indika.
Is it the return address?
0 of ESP would be the return address, right? That's on the top of the stack. It's the first argument because we push the arguments right to left. So this was farther up on the stack, and this is just above the return address. So the EAX is the old, and this one is new. And now how are we saving the old registers? We're just pushing them on the stack. Okay. So we're going to push them on the stack, and then save the old stack pointer into old, star old. So the context is on the stack, and we're just saving a pointer to that context in old. And then this switches the stacks, right, to new. And once we're in new, it's like, how did we get here? We got here from a previous call to this. So what's on the top of the stack? What's on the top of the stack is the stuff that just got pushed. So we're going to pop those things that are on the stack. And then the last thing that was there, we said is return address, so we're going to return. So when we return from here, we're not returning to our caller. Who are we returning to?
Is it the new context?
We're returning to news caller, so to speak, right? Whatever new was when we called switch. Okay. So we come in on one stack, and we come out on a different stack. But the instruction pointer we're not saving. The instruction pointer is still just chugging along. We're just going through and executing instructions. Just returning to a different stack with 4 different registers. So let's kind of look what the scheduler does. So the scheduler has a loop going through the process table. While we're going through the process table, it acquires a lock. Right? So therefore, while we're going through here, are interrupts enabled? No. Through the whole loop, interrupts are not enabled. And what do? We try and find a process that is runnable. So if it's not runnable, we'll just go to the next one. And once we find a runnable process, we will, right, C is our CPU. So we're saying the process that's running on our CPU is this one. Switch UVM does what? Doesn't this one switch the page directory, I believe? Yeah, oh yeah, user virtual memory. That's a good name for that. We say this is running. It's not actually running yet, but interrupts are off, so no one can tell the difference. Interrupts are off, so no other code on this CPU is going to look at that state. And we hold the lock on the table, so no one on another CPU is going to look in at this either. And then we're going to switch. Our rule for switch is you have to hold the lock. You have to hold the process table lock. This is where we're going to store I'm just looking here why we're saving this here. Well, anyway, this is the old, right? This is the new one we want to run. So we're going to run the new one. So let's just kind of look what happens here. When we call switch, are we going to be returning immediately? We are not going to be returning immediately. So we're saving the state because this is the scheduler thread. So this is saving the state of the scheduler thread. And we are going to run this other kernel thread. That other kernel thread, when we return from switch, it's running on its stack pointer. And it's with its saved return address on the stack. And so it's going to some other part of the kernel. And eventually it's going to do an IRET. And eventually we're going to come back in. And eventually there's going to be another switch. And we're going to switch. We're going to come out of here. And we're done with this. So we give it its full, this is not going to return. So it doesn't return until after context runs. Okay? We switch to the kernel virtual memory because we don't care about this user process anymore. Okay? It should have changed its own state. We say we're not running a process, and we go through and find another one. So we just keep going through the table. Now, we are not allowed to hold this lock forever. So we're not going to just keep running through continually through the table. We'll run through it once, and then we'll release the lock. What will that allow? What could happen right after we release this lock, Jonathan? On another CPU. Well, that's possible. Or it could be another CPU was right here in its scheduler thread and wanted the lock, but couldn't have the lock because we had it. Now, one thing to keep in mind is the switch here is going to release the lock sort of automatically. We will see how that happens. Okay, so it's not like this is just going to be held forever. But while we're in the loop itself, it's being held. And so we want another CPU to get a chance at it. And so that's what the release will do. Notice we go right back up and say, well, let's grab it again. Okay? So multiple CPUs will be moderating access to this process table by acquiring and releasing locks. Yeah.
How does switch release and then reacquire the lock?
We'll look.
Okay.
We'll see. We also enable interrupts. The reason we enable interrupts, why do we enable interrupts? Let's think about this a second.
Shouldn't really
Well, yes, so let's look at this. Release will restore the interrupts to the state they were in. So let's look at this second. Oh, let's just try this. What's the scheduling policy? So if you have a thread, a kernel thread that calls yield, is it going to run immediately again? What about if it was thread? Yeah, go ahead. Probably not. If there's anything else to run, it'll run. If that's the only thing to run, yes, it'll run. Okay, so this is good because you don't want one thread to get all the time. Why do we release after the loop? We just talked about that one. Why do we enable interrupts? So here's the reason. We might have a process that was sleeping, waiting for some I/O to complete. We want to make sure the interrupt service routine for that I/O gets a chance to run, and it's going to change that process's state to runnable. So we enable so that interrupt service routine can run and make some waiting process runnable. All right.
If an interrupt happens while interrupts are disabled, will the interrupt service routine deterministically run immediately when you call STI?
The next right before the next instruction after the STI, it should. And what's happening is, in one thread, we're acquiring the lock. This is a complicated, there are two complicated things. So keeping track of which process or which thread is executing where is a little bit complicated because we actually have multiple. We'll come back to that on Wednesday and we'll finish up. We'll look at that and then we'll also look at some coroutines that are used in the kernel.